All right, let's pull back the curtain on the invisible architecture that basically holds our entire digital world together. We're talking about the systems that let you stream, shop, and share everything, all without the internet just collapsing under its own weight. So, how on earth does it all stay online? Now, really, have you ever just stopped and thought about that? Every single second, millions of us are uploading photos, buying stuff, sending messages, all at the same time. How could any one system possibly keep up with that fire hose of traffic and data? Well, the short answer is it can't. So here's the game plan. We're going to start with the original problem, then we'll get into the brilliant solution. After that, we'll see how it all actually works, wrestle with its single biggest challenge, and finally, we'll talk about the real trade-offs that power the modern web. Okay, so to really get why the new way is so smart, we have to understand the old way of doing things and why it was pretty much guaranteed to fail at a global scale. So, in a traditional database, what we call a centralized one, everything, every user, every product, every single transaction, it all lives on one big, beefy server. Just picture one massive, high-tech restaurant kitchen trying to cook and serve dinner for an entire country, all at once.
You can probably see the problem here. It doesn't matter how fast your chefs are or how big your ovens are, at some point that one kitchen just gets completely overwhelmed. Orders start piling up, the whole system grinds to a halt, and you get a lot of angry customers. That right there is the single server bottleneck. It's a hard physical limit.
And listen, this isn't just a metaphor. There's real math behind it. For an early architecture they called shared memory, where you just keep cramming more and more processors into one machine, research showed you hit a hard wall. You'd get a speed up of maybe 37 times tops. And after that, adding more power actually starts to slow the system down because all the processors are fighting over the same resources. It was a total dead end. So, if building one gigantic kitchen doesn't work, what's the move? Well, you don't build a bigger kitchen, you build more kitchens. And that's the whole idea behind a distributed database. A distributed database management system, or DBBMS, is basically the brains of the operation. It's a clever software system that manages a whole fleet of interconnected databases, each running on its own computer. But to the outside world, to the apps, and to you, it all just looks and feels like one single massive database. It's like having a chain of thousands of kitchens all over the world, all working in perfect harmony. And the advantages here are just massive. With a centralized system, if that one server goes down, that's it, game over. It's a single point of failure. But in a distributed system, if one computer fails, the others just pick up the slack, so your availability goes way up. Performance gets a boost too, because data can be stored physically closer to you. And you can scale, well, almost forever, just by adding more cheap computers to the network. Now, the winning strategy for building these things is an architecture called shared nothing. And it's exactly what it sounds like. Every computer or node in the network has its own memory, its own storage. They don't share, so they don't fight over resources. And that completely avoids those bottlenecks we saw earlier. This is the key that unlocks what we call linear scale-up. If you double the computers, you can handle double the data. This is the breakthrough that really makes today's internet possible.
Okay, so we've got a fleet of computers all working together. Great. But how do you decide what data goes where? How do you actually chop up a gigantic database and spread it all over the planet?
The entire goal here is to achieve something called distribution transparency. It really is like a magic trick. For the app or the user making a request, they have absolutely no idea that the data they need might be split across databases on 3 different continents. It just works. All that mind-bending complexity is completely hidden from view. So, let's make this real. Imagine all our data starts out like this. One giant, clean table with all of our employees in it. It's simple, it's tidy, but it's all stuck in one physical place. If our company is global, this is going to be painfully slow for anyone who's far away from that main server. So the solution is to split that table up horizontally. It's a process called sharding. You can see here, we've basically taken all the rows for our European employees and moved them to a server that's physically in Europe. This makes everything way faster for them because the data doesn't have to travel halfway around the world to get to their screen. But what happens if that server in Europe suddenly goes offline? Well, to solve for that, we use something called replication. We don't just store the data in one place, we make copies of it. So if the main server for our EU employees fails, a backup replica can take over instantly. This gives us that high availability we want, and it also helps speed things up, because your request can just go to whichever copy is closest to you.
But, and this is a huge but, replication creates its own massive headache. I mean, if a user in London updates their address, how do you make absolutely sure that change gets made to the copies in Frankfurt and Dublin at the exact same time? And what happens if two people try to update the very same piece of data on two different copies at the same millisecond? This is the central challenge of everything. And that brings us to the hardest problem in all of distributed systems, making sure that even though your data is scattered all over the place, it stays correct, it stays consistent for everyone all the time. Just think about a simple bank transfer. The money has to be withdrawn from your account, which might live on a server in New York, and it has to be deposited in your friend's account, which might be on a server in Tokyo. It absolutely, positively cannot just disappear from one and fail to show up in the other. Both parts of that transaction have to succeed, or both have to fail together. It has to be all or nothing. Now, one of the classic ways to solve this is a protocol called two-phase commit. You have one server acting as a coordinator, and it basically asks all the other servers involved, hey, are you ready and able to make this change? That's phase one. Then, in phase two, each server votes either yes or no. If and only if every single server votes yes, the coordinator sends out the final commit command, and everyone makes the change permanent. If even one server says no, the whole thing gets aborted. But here's the critical weakness. What happens if that coordinator server crashes right after everyone has voted yes, but before it sends the final decision? Well, now all the other servers are stuck in limbo. They've promised to make the change, but they don't know if the final order was to commit or abort. So they're just blocked. They have to hold on to their resources, unable to do anything else, until that coordinator hopefully comes back online, which might be never. So this all brings us to the fundamental trade-off, really the core bargain that's at the heart of this entire field. The incredible power you get from distributed systems comes at an equally incredible price. What you're looking at here is that exact bargain. In exchange for getting almost infinite scale and amazing availability, we have to accept a massive, massive increase in engineering complexity. We're essentially trading one relatively simple problem, a single server getting overwhelmed, for a dozen much, much harder problems, like network failures, synchronization, and keeping data consistent. All right, so to wrap this all up, if you remember just 3 things from this, make it these. First, distributed systems aren't just a nice-to-have. They are absolutely essential for the internet as we know it. Second, that shared nothing architecture is the real key to unlocking that near-infinite scale. And finally, the hardest, most complicated, and most important challenge is, and probably always will be, keeping all of that scattered data perfectly in sync. And that leaves us with one last big question to chew on. We've built these unbelievably complex systems to handle the amount of data we have today. But the amount of data we generate just keeps growing exponentially. So what happens when the scale we need creates a level of complexity that we, as human engineers, just can't reliably manage anymore? What's next?